Good morning, everyone, and welcome to the ITC 2024 Diamond Sponsor Presentation. Our final presenter today is Dan Trock, Principal Engineer at Amazon Web Services. Welcome to the stage, Dan.
Yeah, good morning, everybody. Thanks for having me today. Yeah, I'm really excited to be here. It's really amazing. Every time I come to ITC, I see how quickly things are advancing and moving forward in our field. And Ankur just mentioned that I was here on this stage 2 years ago. I was trying to convince people to get started with SSN and give it a try. And here we are just 2 years after that. You know, everybody's building SSN, right? It just got adopted so quickly, and it's really amazing to see how people build things and optimize on top of it. So today I want to talk about something that we've also built, how surprising, on top of the SSN, and it is the in-system, or as we call it, in-fleet scan testing of silicon chips in our data centers. So, a little background, what is AWS and what kind of chips we are building for ourselves and for our customers. So AWS is one of the largest cloud computing services providers in the world, and we have data centers and huge fleets of systems with silicon chips all over the world. We design and build chips in multiple areas spanning data center infrastructure, core compute, and machine learning. Let's have a look at some of them. Yeah. So with Nitro system, Nitro chips, we accelerated networking and storage and virtualization in our data centers, and we moved the hypervisor functionality away from the host CPU to a purpose-built chip, thus freeing the host CPU to run only customer workloads more efficiently. Then with Graviton we've built host CPUs, and they deliver best price performance for a wide range of cloud workloads. The majority of customer compute today in AWS runs on Gravitons. Inferential Trainium are our purpose-built deep learning accelerators designed ground up to deliver best-in-class price performance and energy efficiency for those who want to run machine learning, inference, and training. So why is in-system test has become so important to us? So we have the early life failures, we have the aging degradation, right? Some degradation going on, and we all know that silicon wears out with time. So we have potential faults from this, and we have potential data corruption faults, right? So it could be a result of aging, or it could be just a test escape. And we all know this, we all talk about it a lot these days. But again, in data centers, we are more sensitive to this kind of problems because of the size and the scale of our systems, right? So imagine a huge HPC cluster or a machine learning cluster. There's many components running intensive computations together collectively, and if even one of these components has some corruption problem, then all of the outcome of the computation can be invalid. Okay, so you would need to restart. So if you're training a large model, for example, this kind of error may take you weeks back in time. Okay, so we want to identify those issues before our customers can encounter them, right? And to do that, we have to test periodically. We have to have a high quality periodic tests throughout the entire life cycle of our products. So it's no longer sufficient just to test production testing and ship the chip and forget about it. No, it can't be done anymore. We have to be there all the time, monitor, test, and till the last day, when we decide to degrade it and remove it from the fleet. So what kind of test can we run in this periodic manner? So clearly the basic is the functional test, right? We run lots of functional tests, it's true. We run it in every stage, in system assembly, in vetting procedures, and particularly periodically in the fleet at every opportunity. We also have some on-chip telemetry, right? We have those monitors that we check, the PVT, the heat, the path margins, and jitter, and all that stuff. And all that is good, but it's still, together with the functional test patterns, it's still kind of, we believe it's just, scratching the tip of the iceberg. That the bulk of the potential life cycle faults is still under the water, and to expose it, we have to do a comprehensive structural deterministic scan test and apply it periodically in the fleet. So this is why we pursue structural and system testing. So here is the design that we've built with in-system scan. It's a large multi-die chip, and we have a center die, a large die in the center, and a few more dies that are small around it. So the table below shows some information about this chip. You can see that the C die alone is more than 100 million flops, and it's quite large. The satellite dies comprise the DRAM and PCI interfaces, and the main die C is very large, like I said, has very few GPIO, and has no high-speed I/O at all. So we do in-system test here on all of these dies, but I want to focus particularly on die C because it's the largest one, it's the most important one. So let's dive a little deeper here. So here is die C with the SSN data path, and when testing in production mode, all test data inputs are injected from the tester through the IOs and aggregated in one central location. You can see it marked in red, the SSN reorder model at the bottom. Everything is aggregated there, and basically in that place, the internal chip SSN data path begins and ends, right? So this is also the place where we put the in-system test controller so that it can easily intercept and take over the IJTAG and the SSN bus clock and data of the chip. Now, this yellow area that you see, this is what orchestrates the in-system testing, okay? So this is a small logic island that keeps running functional during in-system test. And everything outside of this island is fully testable. Internal, external testing, we have full coverage, very close to the coverage we have in production test, okay? So it's just a fraction of faults, this small island. A fraction of faults of the total faults in the die. So let's take a closer look what's going on there. So we have the peripheral bus system, the PBS. It receives test data from the external microcontroller and constructs a chip internal transaction towards the in-system test controller. The in-system test controller converts this transaction into, it's typically a write transaction, it converts it into a bus access cycle. So every write transaction is basically translated to one cycle of SSN bus clock and data. And we stream those write transactions one after the other very efficiently because it all goes to the same address, right? So during test payload application, we optimize here. And now, like I said, this die has no high-speed I/O. So what we have on this chip is an SPI, and we enhance it a little bit to quad SPI, running on four data lines in parallel, and we run those lines at relatively high clock frequency so that we achieve a decent test bandwidth, maybe not as high as with a high-speed I/O as it could be, but it's still not bad. So with this setup for a die like this, we can apply a full scan test program similar to the one in production in about few minutes, okay? So if you're an idle CPU now waiting for being sold to your next customer, we can run this test on you, we can check you, and we can do it every once in a while, and we can do it also on the other CPUs, and eventually on the complete fleet, right? So this is a very powerful capability. This is exactly what we wanted to achieve. We wanted structural, deterministic, full scan testing in the fleet, and we get that visibility into what's going on in the fleet and this lifecycle monitoring, and this is what we wanted. So let's summarize. So we've built a structural, deterministic, in-fleet test into a large multi-chiplet design. We haven't compromised on coverage. We achieve almost the same coverage as in production, and it includes internal and external mode testing. We improved lifecycle monitoring, fleet quality, and reliability. We have full scan diagnosis now in the fleet, which is also a very powerful thing because, you know, once you have a problem, you typically, what you do, you need to authorize the return of merchandise, you know, you need to get that chip back into your lab and start checking it, what's going on, etc. And it usually takes weeks or months even until you get your hands on the unit, right? So with in-system scan, we can run diagnosis directly and hopefully even localize the fault without removing the chip from the fleet. Okay, so it's also very, very powerful. And all this, of course, is based on the common SSN technology layer that we use for both manufacturing tests and in-fleet tests. We generate those patterns just once, and then we retarget them either to the I/O pads for the tester or to the in-system test controller for the fleet testing. Okay. So if you're interested in more details, we have a nice paper, and please read. And you're welcome also to attend the industrial track session on Thursday, where I'll dive a little bit deeper into the details of this work and present maybe some more interesting related findings that we didn't have time to discuss here. Okay? Thank you very much, and have a nice test week.